Hello, I'm Steve Fry, a member of the Dayton Microcomputer Association and a longtime contributor to the Dayton Computer Museum. The Dayton Computer Museum has been a participant in Tech Fest since the first one in 2003. It's been there every year with a display of classic computers, largely from the 70s and 80s, a lot of the early home computers that people had, as well as older stuff that goes back into the mainframe, vacuum tube age, core memory, mini computers, and even a little bit of stuff that's newer than that. And the Computer Museum goes back even farther than that. It's been curated by Gary Ganger for a long time, and it's largely stuff that he had himself and stuff that's been contributed by members of the association over the years. As they get a new machine, they would pass the old machine off to the museum. So that's been partly where some of the stuff comes from. And then people like me also contribute their own collections to the exhibit when the museum is set up at various events. Usually we have a long table full of stuff and people can look at it. And one of the big comments that you see going on is the parents showing the students, their kids, I had one of those and I did this on it and this on it, and if we have it turned on and running, they can actually do something on it. And it's kind of an interesting exercise along those lines where they have a personal connection to a particular item in the museum. So anyway, this is a TI-99-4 A computer that I've had since about 1981 probably. I previously had a 99-4. And one of the interesting things about this machine is that it was one of the earlier home computers that was actually a 16-bit processor. And one of the things that attracted to me was the fact it did the double precision, high precision math on it, scientific notation, 15 digits. So that was kind of unique to some extent, but other ones could do it with the software. Over here, I have a Altair 8800B on the exhibit here. And this machine came from the David Steele collection. I restored it in late 2019 and going into 2020 and had it operating at the 2020 Tech Fest, which I'll show a picture of it at that time. It's in fine shape right now. It runs fine. It took a little bit of work to restore it, replacing switches and cleaning up power supplies and doing a lot of cleaning up on the ICs on the circuit boards and getting the circuit boards in there and getting it all operational. So I'll be doing another video on it at some point in time on the restoration process on that. And of course, with any museum, it's also good to have the documentation to go along with these things. So this is just one of my binders of documentation on the Altair 8800B. It was the successor to the 8800, which is credited with starting the home computer, microcomputer industry, and also, of course, Microsoft, because Bill Gates and Paul Allen developed the basic for that, and that's really what started Microsoft. And one of the ones that came after, or about the same time in there, inserted between the two, was the Altair 680, and that's actually the first one built by the Dayton Microcomputer Association on one of the members' kitchen table. And that's kind of got the organization going a long time ago, 75, 76. On the TI, once again, you got to have documentation on things. So there's documentation, even circuit diagrams, a reference for it. I use mine for actually a lot of work type stuff. There's Microsoft Multiplan, so it's a spreadsheet. And then here was an interesting little bit of artificial intelligence out of MIT. Logo, which was developed as an educational program for people to learn programming, and you could control turtles and stuff like that, and by typing in your lines of code you could move things around on the screen. And you can actually have a mechanical turtle hooked up to it. So that was an interesting product. So I'm going to move some more things into display here and show you some more items like we're going down the table. Well, back a little bit farther into the past, this big thing here is a COM-1 minicomputer. 16-bit processor running at just slightly faster than 1,000,000 instructions a second. Core memory on the machine. It has each one of these sections right here. How well you can see it, but each one of these is 8K by 17, and there's two more, so there's 32K of 17-bit words for the memory, and the logic on it. These are all called planes, and you can raise the planes up and access the circuitry. There's the loop controller and serial port stuff, and then the next one down is actually the CPU. It's all TTL logic, wire wrapped. I should have this oriented so you can see all the wire wrap. But this particular machine has an interesting history because it was the first computer controlling the original building automation system at Wright State University, 1975. And it controlled the campus air handling units and chillers and boilers, provided monitoring and overall, start-stop scheduling, stuff like that, for maybe a year or two. And the way Wright State was growing at that time, adding buildings, it didn't take too long before it was not big enough to handle the job. So they put a bigger computer in to handle it. Another Modcom, and Modcom 2. This one was bought back from Wright State to use as a backup computer, and it was used as a backup computer all the way through about 1997. This one still operates. Core memory is fantastic. You turn it off and you wait 10 years and turn it back on, and guess what? The program's still there. It's all stored in magnetic field inside the little donuts. Showing you what that looks like. This is a smaller one. This is from a 1965 Burroughs B300/B500 mainframe computer. This has got 4,800 bits, and these were stacked in there like 7 of them to provide a 7-bit word of 4,800 of them. So that's what the core memory looks like. Little donuts on a bunch of little wires. You can check that out on the internet, see more about those. That was the first kind of memory which really was successful in computers. Everything else is not that reliable, and that was the first time when they got to the point where you could have pretty high density. This is a Fabritech core plane. If you take the cover off, you see a whole bunch of sections of minute little teeny tiny donuts. You practically got to use a magnifying glass to really see the donuts in there. That's from Fabritech. Same company that does the core memory that's in my COM-TRAN TEN I've been restoring for the last year. Or actually on and off for 4 years. Here's documentation on the COM-TRAN TEN I'm restoring. And that's what that monster looks like. Maintaining old computer systems and restoring them and using them is called vintage computing. I'm going to show you a little bit of retro computing here in a moment. And this is getting into, I actually had this manual here I found online. It came from Keesler Field. The COM-TRAN TENs were used by tech schools. The one I have came from Cincinnati Technical College. Was rescued, somebody had it in their estate. It was rescued by the Reese family, and I got it from the Reese family. So it's from the Reese family collection, and I've been restoring it. But I've been having to go through and trace out all the circuitry in this thing because this book, while it gives me enough information to do the job, doesn't provide the schematic diagrams that it refers to. They're in another manual. So I'm looking for the schematic manuals for the COM-TRAN TEN training computer. It's a big mini computer with little capabilities that was used for training people on how to do the repair work on these. Going back a little farther in time, here's a 10-bit address counter. This is getting back to single transistor logic, whereas this is TTL, and you have a number of gates on each one of these ICs. This is getting back to individual transistors, and this is actually 10 flip-flops for a 10-bit counter. This would be back in the 60s. This was state-of-the-art 1972-73. This is also back in the 60s. This is from a GE 645 computer. I haven't figured out what it is yet. It might be another counter. It's an interesting computer. It's a 36-bit computer, and they broke things down into either 9-bit words or 6-bit words, and this has got 6 circuits that are repeated across it. And going back a little farther in time, I'm not sure how well you can see it back there, but this is vacuum tube based, going back to vacuum tubes. So these are 2 event counters. It counts, I get 2 of them hooked up, each one counts to 10, 0 rolls back to 0. And when this guy rolls over, it sends a signal to pulse the second one. So it carries it over and pulses the second one. These were used for frequency counting, for event counting, and they could go up to about, this one could go up to 100 kilohertz, and there were versions of them that went to 1 million megahertz using vacuum tube technology. So we can get into vacuum tube technology in the computer, how the computers used them. These each have 4 tubes. There's each tube is a dual triode, and therefore each one can function as a flip-flop. So there's 4 flip-flops there, and I'll get into more on flip-flops in another program. So that's getting back about as far as I'm going to go on that stuff, and then I'm going to move over to another part of the presentation. Now, this is called retro computing because it's making something new using an old technology. In this case, it's a relay-based computer. It's built with 198 relays, little double-pole, double-throw, 5-volt relays that fit dip sockets, and a lot of diodes, 500 and some diodes. It has 32 dip switches, 8-position dip switches, and those are used to set the 1s and 0s for each of the instructions, so it can run a 32 instruction program off the dip switches. This part of the unit is a control unit that generates all the timing and address selecting and branching and all that stuff. And this is the data side of the computer. Has a 16 function ALU. Has 4 general purpose registers and 1 register set aside for handling the robot interface for input and output of 4 bits. A data console for putting numbers in, and the timing generator circuit over here is what generates the instruction cycle. I'll get into more detail on this thing on a future video, getting into all the logic and how AND gates and OR gates and all this stuff goes together to build a computer, and how this particular computer works and all of the programming of it and that kind of stuff. It does have an interface on the back side of here to either use my paper tape reader off of a teletype. I took that off of there, and there's a sample of a program that basically tests all the functions of this ALU. Doesn't take very many bits to do that. And so it can run programs off the tape. It can go back and forth between the tape and the switches, or you can switch and run in a mode where it just runs off the tape, and the counter over here, instead of being a up counter, can become a down counter, and it'll actually do skips on the tape. It'll say the branch instructions become telling it how many instructions to skip on the tape to make decisions. And then you can have a program of any length you want, because it just depends on how long the tape is. And if you want a loop, you just basically have to tie the end of the tapes together and make it so it goes around in a loop. I can also use my Heathkit paper tape punch reader that I assembled back in the 70s and used with my homebrew mini computers. And so I can punch the tapes with that using this data console, and then run the tapes on that also. So coming in a future program, you get to see how this all functions. So that's it for now from the Computer Museum.